All right. So you want to have your notes out.
Are we on D?
We are on D. Yes, the vibration of wave particles. We've only got a handful of slides to go. So as this is getting ready to warm up, yesterday we started talking about waves and getting to understand the fact that waves are actually energy that is moving throughout space, throughout a medium. And so it's not that the wave molecules are moving along, or the water molecules aren't moving along. It's that they are essentially moving up and down because of energy, and they are helping to move that energy along. And as that energy, or as those waves move further and further away, they tend to lose energy, and eventually the energy will run down. So this brings us to today, okay, the vibration of wave particles. So as a wave moves, particles are going to be vibrated in a similar way that those connected masses move. We talked about those connected masses yesterday. The damped ones, where we had the masses that were attached by a string or spring to each one. Well, that's what's going to happen. They're going to affect each other, but if no additional energy is going to be put in to their vibration, they're going to eventually slow down because they're impacting each other. An example we can see is if we have a rope that's moving up and down connected to a doorknob. As you move the rope up and down, you will generate a single wave. Okay, if you do that little whip action on the rope, you see that wave go down. As that wave moves along the rope, each part of the rope moves up and down, but it eventually goes back to its original position. As one part of the rope moves, the wave passes along the length of the rope by pulling on the next part of the wave. So again, as you see here, looking at this image here, we got red and green locations. As we flick our wrists and send the wave down, those locations, those red and green locations, they stay in the same spot. They don't move along with that wave. All they do is move up and down, but their location is going to remain the same. And the reason why that wave is allowed to move down that rope is because one particle is connected to the next, is connected to the next, to the next, and so on and so forth, to where they move each other. But if you only do that one flick of the wrist, eventually that wave will dissipate because you have not put in any more energy. Yesterday we mentioned a couple terms, transverse and longitudinal waves. Today we're also going to introduce surface waves. So in order to classify waves, we have to look at how they move. When particles are moving in a medium, they can vibrate either up and down or back and forth, or sometimes even a combination of up and down and back and forth. So the waves are classified according to the direction in which the particles in the medium move as that wave passes by. Now those longitudinal waves, or those back and forth waves, we saw if you think about a slinky or a big giant spring, and you're constantly stretching and compressing, okay? That would be like a longitudinal wave. So again, there's three types of waves: transverse, longitudinal, and surface. Let's see if I can't. So just so you can see, a surface wave would be like an ocean wave. Okay? They are right at the boundary between air and water. This red little thing here, up and down, that's a transverse wave. And this blue coil or spring-like, that is a longitudinal wave. Okay, so let's look at transverse waves first. The transverse wave is defined as a wave in which the particles of the medium move perpendicularly to the direction of the wave that is traveling. So much like we saw with the rope. Okay, the wave is traveling from the person's hand to the doorknob. So it's going horizontally. The particles, however, are vibrating up and down. So they're somewhat moving in perpendicular directions between the vibrations of the particles and the motion of the wave. Electromagnetic waves are transverse waves. Electric and magnetic fields that make up an electromagnetic wave are perpendicular to each other and to the direction in which the wave travels. So we got the rope on the doorknob, we've got electromagnetic waves. Those are examples of transverse waves. Longitudinal waves. These waves are defined as a wave in which the particles of the medium vibrate parallel or in the same direction as the wave motion. Slinky or spring are great examples. As you move the slinky or spring back and forth, the wave will travel along that spring. As this wave passes along the slinky or spring, the spring will coil and move back and forth parallel into that direction. Okay, I think I got signed out here. That looks better. All right. So in a longitudinal wave, we're going to have areas called compressions and refractions. Or it's actually supposed to be, rarefactions. This is a typo. It's like, that doesn't look right. So yes, it should be compressions and rarefactions, not reflections. Fractions. See, now it's confusing me. Compressions are the crowded areas. So if you look at this image over here on the right, where you have these coils that are closely put together, those are compressions. Then you have rarefactions, where the areas of stretched out areas in the longitudinal waves.
So it's the bottom one that's directly stuff.
Yes, the rarefactions. Looks like me, David. I can't even click it. I want to go back. Oh, okay.
Longitudinal.
It should be our last slide. Okay. And then we have surface waves. So the particles in the surface wave move both perpendicularly and parallel to the direction in which the wave travels. These waves are virtually a combination of transverse and longitudinal. They occur at the boundary between two different mediums, so water and air in this case. And the shape in which they move is what we call an ellipse. Okay, it's circular, but not a nice and perfectly round circle. Okay, it's got a little bit of extension, almost oval-like on there. Anyway, if you look at a beach ball, I'm trying to move this. If you look at a beach ball that is caught out in the ocean, okay, the wave itself is in these images is moving from left to right, and at first the ball is in a trough. It's in between the two waves. So as the crest approaches the ball moves to the left. Even though the wave is moving to the right, the ball moves to the left, which is parallel to the wave. Then it moves upward, which will be perpendicular to the wave. When that ball is near the crest, it then begins to move to the right. So here we have the ball in a trough. It moves to the left and then up. And then once it gets to that crest, it begins moving back to the right. Once that crest has passed, as we see in the second to last image, the ball starts to fall back downward towards the left, back into the trough. And so when you combine all of these movements together, the ball is moving in an ellipse or circular pattern. So it's kind of weird watching this happen. Okay? The ball moves opposite the wave is moving, and it does not move. It's much like what we saw with the leaf that was on the pond yesterday. Okay? As waves go past the ball or past the leaf and ball will move in a fashion, but it'll remain in its current location. And that is it for section 1. So again, I'm going to post this video and just submit your assignment to this post, and it's going to go up here in a little bit. I think I'm going to have extras today. Extra hard copies, that is. By the way, if you ever need any hard copies printed, just give me an email or whatever, and I'll have it ready and down at the table in front of the office downstairs. If you ever need anything printed.
I'll be coming in for ag construction, so if you, I might come up here and just check to see if you're in the
That's fine.
anything like that.
And if it's not, just you can just send me an email saying, I'm going to be up there doing anything, and I'll try to make sure that I either have it ready for you then, if I'm not here, or if I'm here, I can get it for you. But there shouldn't be too much in the next week or so that's going to be hard copies. So, there will be one more thing tomorrow, but it's not very long. It's like one page. So I know you're still writing down some of these. I'm just going to stop filming for now. So you should still be able to see it. Oops. Oh, no! That's not what I wanted. I'll get back there. Okay.